instead of the divisor 2, if I take b and 4, which is the quotient, I can write q itself, and the remainder 1 I'll replace it by r. Now I'm trying to generalize so that we can write this using variables. So now it will look like, how will it look like? It will be a equal to b q plus r, and this is same as dividend equal to divisor into quotient plus the remainder. So there is nothing here. This is almost like 5th, 6th standard level, 5th, 6th grade level discussion. We are just going to give it a different name to it, like Euclid's division lemma. What it's all about, you will understand very soon. And there is nothing new. We are just going to give it a new name. This generalized using variables is called Euclid's division lemma, which is nothing but, if you state that, it will be like this. Given positive integers a and b, there exist unique integers q and r satisfying a equal to bq plus r, where 0 less than or equal to r less than b. That is, the remainder r can be 0, but it will be less than the divisor b. Now, going back to the chocolate example, we had set the first example, we had 7 chocolates. So once you fix that number 7 and 3 chocolates per box, that's also fixed, then it is obvious that the number of boxes which you can take and the left out chocolates, they are also getting fixed by default. That is why the word unique integers is used in this explanation, because as there will be only one set of solutions. It's very easy to understand. I hope you are getting it. What is that? In that example, when the number of chocolates are fixed, when the number of chocolates per box is fixed, the number of boxes which you can take out is also getting fixed, and what is going to be left out, and number of chocolates, that's also getting fixed. So there is actually nothing new. This is something which you've been doing for quite some time now. We have just given it a new name. Maybe the name is a bit complicated, but the concept, the pattern, and because of that, even the questions which are going to come based on this is going to be well below your level. You need to understand that. So there is nothing to be scared about Euclid's division lemma. Now, rather than using a scenario, let me directly give you an example over here. An example for division. If the numerator is taken as 16, that is the dividend if it's 16, if the divisor, if it's fixed at 3, then you are anyway fixing the quotient as 5, what you will get as the answer, and you are fixing the remainder as 1. So same thing can be written as 16 equal to 3 into 5 plus 1. So there is nothing new here, as it's proved once more. And it's just a presentation, it's just a new kind of a presentation for the same old division, which all of you are already very comfortable. Let's look at some more examples just for practice. So if I write what is division lemma? A equal to bq plus r. I'm going to put this in a box. The first, that A is dividend, then equal to divisor into quotient plus the remainder. I'm just going to fill these 4 boxes with some examples over here. So the first one which I discussed was, so if I write 7 here, 7, and if I write 2 here, so 7 and 2, quotient will be 3, and that's fixed at 3, remainder is fixed at 1. If I take 14 here and 6 here, then this is fixed at 2 and this is fixed at 2. So if I take 17 here and 6 here, quotient is going to be 2 and the remainder is going to be 5. Now I can also write a number which is where the dividend is less than the divisor also. If I write 5 here and 12 in the divisor box, then the quotient will be 0. It's perfectly fine. It can be 0 and the remainder will be 5 itself. Now even the remainder can be 0. Let me give you an example over here. If it is 20 in here, 20 in dividend, and if I put 4 as the divisor, quotient will be 5 and the remainder will be 0. So these are just some basic examples using numbers so that you understand Euclid's division lemma. So this is same as A equal to BQ plus R, where if A and B are integers, then you will have Q and R which are unique, where R will be between where 0 less than or equal to R less than B. It's very, very simple. I hope this much is enough for all of you to understand. Next, I'm going to discuss something very important, Euclid's division algorithm. Let us look at an application of Euclid's division lemma, which all of you know that very well now, and it's called Euclid's division algorithm, the application. So we are basically taking it one step further. The application is a technique that will help us find the highest common factor, which is, or the HCF. Now, what is an algorithm? If I ask you that question, it is nothing but, it is actually a series of well-defined steps which gives a procedure for solving a particular type of problem. So, and how is it different from lemma? You heard that word now. And what does lemma mean? It is a proven statement used for proving another statement. So now you would know how to find out HCF by prime factorization. That's not what I'm going to discuss right now. Right now I will show you how to find out the highest common factor, which I'll denote as HCF, using Euclid's division algorithm, which is actually an application of the lemma. So first of all, this method is very useful for calculating HCF of very large numbers. And why it's even more interesting is, this is actually one of the earliest examples of an algorithm that a computer had been programmed to carry out. So let's understand this first using numbers, so that all of you will get a clear idea how it works. And it's going to, because of that, it will become very simple. And then we will generalize it using variables. We will visualize it in a diagram, and we will discuss it using words in a lot more application-based questions on Euclid's division algorithm. So that's what I'm going to do next. First, I'm going to make it easy for you by using some basic set of numbers, where I'll help you find out HCF of those numbers by using this new method. It's new, but it's going to be very old very soon, because all of you are going to understand this in a matter of in a couple of minutes. So let's take two basic numbers, 60 and 36 first, so that it's very easy to understand. That's why I'm starting with some basic numbers. So let's find out HCF of 60 and 36 using this new method, which I meant to discuss. So 60 and 36, apply Euclid's division lemma. So when I say apply Euclid's division lemma, what you are supposed to do is, you write 60 equal to 36. You are basically considering a division of 60 by 36, but I'll represent it in that format of A equal to BQ plus R, where A is the dividend, B is the divisor, Q is the quotient, and R is the remainder. So if I express it like that, that's the meaning of applying Euclid's division lemma. That's nothing but division in a different format. So 60 equal to 36 into 1 plus the remainder is 24. Now, what will happen is, here the divisor 36 and the remainder 24, this divisor you take it as the next dividend, and the remainder will become the next divisor. So that is what you are supposed to do next, and you, by keeping this, apply division lemma once more. So it will become 36 equal to 24 into 1 plus 12, and you will continue doing this till you get the remainder as 0. And when you get remainder as 0, that will be the last step. In that step, whatever be the divisor, that will become the highest common factor of the first two numbers which we started off. So let's continue doing this, and it's a very simple process. What we did is, let me repeat. We started with 60 as the dividend, 36 as the divisor. So 60 equal to 36 into 1 plus 24. One example is enough for all of you to understand this. So listen carefully. So next, this 36 divisor will come here, and 24, which was the remainder in step 1, that will become the divisor here. So 36 equal to 24. So you are supposed to take 36 by 24 and write the quotient as 1, because 24 will go once in 36. So 24 into 1 plus 12. Repeating that is nothing but you just see what is happening here. 24 will come here, and that is the dividend. 12 will become the divisor. So we'll write 24 equal to 12 into 2 plus 0. So here itself, the remainder is becoming 0. So the current divisor, that is in the last step, which is 12, will directly become your answer, or that is the HCF. Now this particular, so this procedure here, this is the series of procedures is helping you to find the HCF, and this is called Euclid's division algorithm. And it's a very simple process. What the divisor in every step, the divisor will become the next dividend, remainder will become the next divisor. Continue doing that till the remainder is becoming 0, and in that step where it's becoming 0, divisor, take it as the HCF. And it's so easy that I'm very sure that by this time, we just look at the screen itself, all of you will understand how to find HCF using this new method. Now, if you simply want to state Euclid's division algorithm, if you want to state this using variables, we just need to generalize what we did now. It's not required anyway, but this is as given in the book. If you simply want to state, this is how it will come. This is what you are supposed to do. So let's try putting variables here. To obtain the HCF of two positive integers, let's say C and D, you follow the steps given below. What was the first step? Step 1 is apply Euclid's division lemma to C and D, so that you can find whole numbers Q and R such that C equal to, C is the dividend, C equal to D Q plus R. So you are getting Q and R. Now continue the process. You need to continue this process where next here the divisors D will become the next step, D will become the dividend and R will become the divisor, and continue doing this till R will become 0, and when R is becoming 0, in that step, whatever be the divisor, that will become the HCF. So this is how you can state Euclid's division algorithm using variables. Since that you already understood Euclid division algorithm, let's try one more example over here, and I'm sure all of you will get the answer right here. Try finding out HCF of 24 and 15 using Euclid's division algorithm.